Welcome, students. Today, we delve into a fundamental yet intriguing problem in the realm of algorithms, the two-sum problem, which is recognized as Problem 1 on LeetCode. In this exercise, you are tasked with identifying two distinct numbers within an array that, when combined, yield a specified target sum. The input consists of an array of integers along with a target integer, and your objective is to uncover the indices of these two numbers. To illustrate, consider the input array 2, 7, 11, 15 with a target value of 9. The solution lies in the numbers at indices 0 and 1, which are 2 and 7, respectively. These two values sum to our target of 9, leading to the output of the indices 0, 1. As we explore this problem, we will uncover various methodologies and their efficiencies, enhancing our understanding of algorithmic design. Let us embark on this intellectual journey together. Hashing for index mapping is a crucial technique that transforms data into a fixed size value known as a hash code. Think of this hash code as a unique address where data is stored in a structure like a hash table. When we input a key, a hash function processes it to produce this hash code, which tells us exactly where to find the corresponding value in memory. The beauty of hashing lies in its efficiency. Imagine searching for a book in a huge library. Instead of scanning every shelf, you go directly to the shelf indicated by the book's catalog number. This is similar to how hashing allows us to retrieve data quickly, ideally in constant time, or O1. However, sometimes different keys might produce the same hash code, leading to what we call collisions. To handle this, techniques like chaining or open addressing are used, ensuring that we can still access all the data efficiently. By understanding and applying hashing, we can optimize how we manage and retrieve large datasets effectively. Here we have a function that maps elements to their indices using hashing. In programming, this is particularly useful for quickly retrieving the position of an item in a list. First, we initialize an empty dictionary called indexDict. Think of a dictionary as a real-world phone book, where each name or key is linked to a specific phone number or value. Next, we loop through the list of elements using enumerate, which gives us both the index and the element itself. As we go through the list, we add each element to our dictionary, using the element as the key and its index as the value. This way, we create a mapping of each fruit to its position in the original list. Finally, we return this dictionary, which in our example allows us to see that apple is at index 0, banana at index 1, and cherry at index 2. This technique is efficient and makes lookups very quick. Understanding this concept is key to solving problems like the two-sum challenge. The two-pointer technique is a strategic way to tackle problems involving arrays or linked lists by using two distinct pointers. These pointers can start from opposite ends or the same position, depending on what you're trying to achieve. The main idea is to efficiently search or compare elements, often achieving solutions in linear time, which is much faster than using nested loops that can lead to quadratic time complexity. This technique is particularly useful when you're looking for pairs of elements that satisfy certain conditions, merging sorted arrays, or even checking for palindromes. By starting with two pointers and adjusting their positions based on specific criteria, you can simplify the code and significantly cut down the number of operations needed. For example, if both pointers start at the ends of an array, they can move towards the center, allowing you to compare elements from both sides simultaneously. This not only makes the solution more efficient, but also helps in handling larger datasets more effectively. The two-pointer technique is a powerful method used to find pairs in a sorted list that sum up to a target value. In this function, two-pointer sum, we start by initializing two pointers, one at the beginning of the list, called left, and the other at the end, called right. As long as the left pointer is less than the right pointer, we calculate the current sum by adding the values at these two pointers. If the current sum equals the target, we found our pair, and we return it. If the current sum is less than the target, it means we need a larger value, so we move the left pointer to the right to increase the sum. Conversely, if the current sum is greater than the target, we move the right pointer to the left to decrease the sum. If we finish checking all possible pairs without finding a match, we return none. This technique is efficient and works well because the list is sorted, allowing us to strategically narrow down our search. A frequency array is a powerful tool for counting and storing occurrences of elements in a dataset, like an array. Imagine you have a box of colored marbles, and you want to know how many of each color you have. Instead of counting each time you need to know, you could create a chart. This is similar to a frequency array. Each index in the frequency array represents a specific color, and the value at that index tells you how many marbles of that color are in the box. This method allows you to quickly answer questions about your marbles, like how many blue ones you have, without searching through the entire box each time. Building a frequency array involves a single pass through your dataset, taking O(n) time, where n is the number of elements. After this initial setup, you can answer queries about element counts in constant time, O(1). This efficiency is invaluable for tasks like inventory management or analyzing data, turning potentially slow operations into quick lookups. Let's explore how to create a frequency array using a function called frequency array. This function takes a list of elements and counts how many times each element appears. First, we initialize an empty dictionary called freqdict. Think of this dictionary as a tally sheet, where we'll keep track of each item's count. Then, we loop through each element in the input list. For each element, we use the get method of the dictionary. This method checks if the element is already in our tally. If it is, we add 1 to its current count. If not, it starts at 0, and then we add 1. Finally, once we've counted all the elements, we return the frequency dictionary. For example, when we input the list of fruits, 3 apples, 2 bananas, and 1 orange, the output will show how many of each fruit we have. This method allows us to quickly look up how many times an item appears in the list, making our search efficient and straightforward. The two-sum problem requires us to find 2 numbers in an array that add up to a specific target. Let's break down the solution step by step. First, we need to understand the problem clearly. Given an array of integers and a target integer, our goal is to identify the indices of the 2 numbers that sum to the target. To solve this efficiently, we'll use a hash map, also known as a dictionary in Python, which allows us to store numbers and their indices. This makes our lookups very fast. We start by initializing an empty hash map. As we iterate through the array, we calculate the complement for each number, which is simply the target minus the current number. Next, we check if this complement already exists in our hash map. If it does, we found our solution and can return the indices. If it doesn't, we add the current number and its index to the hash map for future reference. This approach only requires a single pass through the array, giving us an efficient O(n) time complexity while maintaining O(n) space complexity due to the hash map. Here's how this looks in Python. We define a function toSum, where we loop through the numbers, calculate complements, and check for matches in the hash map. This method ensures we find the 2 indices quickly and effectively. In this problem, we are tasked with identifying the indices of 2 distinct integers within an array that sum to a specified target value. Notably, the array contains at least 2 elements and can grow to a maximum of 10,000 elements. Each integer ranges from -10^9 to 10^9, including the target itself. A critical constraint is that each input guarantees a unique solution, and we cannot use the same element more than once. With these parameters in mind, we can develop an efficient approach to derive the solution. The provided Python code addresses the well-known toSum problem, which seeks the indices of 2 distinct elements within a list that sum to a specified target. To solve this efficiently, we use a hash map called num_to_index, which allows us to access values quickly. The function toSum starts by initializing this empty dictionary. As we loop through the list nums, we get both the index and the value of each element. For each number, we calculate its complement, defined as target-num. Now, the key part of this algorithm is checking if this complement is already in our hash map. If it is, we immediately return the indices of the complement and the current number. This guarantees the indices are distinct because we only store numbers we've seen before. If the complement isn't found, we add the current number and its index to our hash map. This strategy optimizes the search process, allowing us to find the required indices efficiently while keeping space usage minimal. This approach aligns perfectly with best practices in algorithm design. The time complexity of the two-sum problem is O(n). This means that our solution scans through the list of numbers just once, looking for two numbers that add up to the target value. Imagine you're searching for a specific book on a shelf. If you check each book one by one, the time it takes will grow in direct proportion to the number of books in the shelf. Similarly, as the size of the input array increases, the time required to find the solution increases linearly. Now, let's discuss space complexity, which is also O(n). In our solution, we might use a hash map to keep track of the numbers we've seen and their indices. Think of this hash map as a sticky note where we jot down each book's title and its position as we look through the shelf. In the worst-case scenario, if all numbers are distinct, this hash map could grow to be as large as the input array itself. Thus, our space usage can also increase linearly. Understanding these complexities helps in evaluating the efficiency of our algorithm.